In this video, we're talking about statistical inference with error plots. This will allow us to go beyond just representing the results of studies and experiments into making inference from our data for what the state of nature is, what's actually going on biologically. So error plots are used to characterize the differences between groups. We have two categories here, two different types of families. We have a numeric variable height along the y-axis. These data are from Francis Galton on the heights of different families. So when the confidence intervals of two groups, we have a group here with a mean down here, we have a group here with the mean up here represented by the dots. When the confidence intervals of two groups, particularly the 95% confidence intervals, everything I'm going to say in this presentation only applies to 95% confidence intervals, does not apply to error bars from using standard deviations, does not apply to error bars using standard errors, definitely does not apply to the whiskers from box plots. Just when the 95% confidence intervals of two groups do not overlap, we can say they are significantly different or statistically significantly different. And this allows us to infer that perhaps there is a consistent real biological difference between these groups. Again, it's important to emphasize that there are significantly different statistically. Can't emphasize this enough. It is a statistical statement that we are hoping to make about what's actually going on in the real world biologically, but it is just a statistical statement. It does not mean that there is a real, true difference inherently in nature between the groups that we're investigating. If we were to do a formal statistical test, such as a t-test, which would be appropriate for this data, the fact that the confidence intervals don't overlap would mean the 95% confidence intervals don't overlap. That would mean the p-value would be less than 0.05. So p would be less than 0.05. We'd have to actually do the math or use a computer to determine how small the p-value is. P of 0.05 is a usual cutoff for using the term statistically significant. So when confidence intervals, 95% confidence intervals, overlap a lot, that means that the means are not significantly different or not statistically significantly different. How much they overlap, there's some rules for understanding that, but it's best to just, as a rule of thumb, that if they overlap a lot, if they overlap completely, then they are not significantly different. If we were to do a formal statistical test using a t-test in this case, that means that the p-value would be greater than 0.05. It'd be a lot greater than the traditional cutoff of 0.05. Those of you who are taking this as a class should prepare to pause the video in order to answer the following question. Looking at these three graphs here, which set of graphs shows a statistically significant difference between two means? Is it graph A on the left, graph B in the middle, or graph C on the bottom? Which graph indicates a statistically significant difference between the two groups? Go ahead and pause the video and answer that on the course software. So the correct answer to this is graph A. The error bars do not overlap at all. Even if they just barely touched each other, they would still be a significant difference between them. In both of these other cases, graph B, the error bar here is equal to or lower than the mean, and here there's significant overlap. So in both of these cases, the p-value will be will be greater than 0.05. A p-value of greater than 0.05 indicates a non-significant difference. In this case, in graph A, the p-value will be less than 0.05. We can say there is a statistically significant difference between the means. Cannot be emphasized enough, significance is a statistical concept, not a biological one. It does not mean that the difference we see would occur again if we had a larger sample size, if we repeated it in a different population, if we repeated the exact same experiments as best we can. It does not mean there is a real, important, valid biological difference. It just means statistically the data are significantly different. Cannot hit this home enough. This occurs so many times, even in biology textbooks and biology papers. So many people confuse statistical significance with a real, relevant biological difference. So I'll keep repeating this. Significance is a statistical concept, not a biological one. Repeat it with me. Significance is a statistical concept, not a biological one. In order to understand the biological relevance of the difference, you need to understand more of the biology and make sure all your ducks are in a row in terms of a good sample size, a good representative sample, and understanding the biological mechanisms and biological importance of the difference you're seeing. So to break this down a little bit, when we say that there is a significant difference between these means, that we can interpret that as meaning that if Galton repeated the experiment, he'd expect to get similar results. He'd expect to have the means be a similar but not exact same difference. However, it doesn't mean that anything interesting is going on biologically. We'd like to infer that something in nature is causing heights to be significantly different, but we can't know for sure whether it's true, and we can't know for sure whether if we repeated the experiment, we'd get the same difference. So we'd expect to get similar data, but we can't be guaranteed different data. We can infer that something in nature is causing these differences, but we can't be certain without doing a lot more work. So again, significant does not tell you about biological relevance. It doesn't tell you about biological reality. For example, in this data set, there's a significant difference between these groups. This group is a little less than 67.5, we'll say 67 inches. The 6 or more group, 70.2 inches. When I worked up this data, the hypothesis that I was playing around with is that one-child families would be able to devote more resources and their children would be taller and healthier. Larger families would have fewer resources per child. However, I don't actually know what resources were allocated to these families or to these children, what resources they had available to them. I'm just making a step. I'm making a guess that these families differ in the resources they could devote to feeding their children. Also, biologically, is a 4 or 5 inch difference relevant to humans? Not really. There might be something going on here, but a 4-inch difference does not really make a difference to most people's ability to do work or survive day to day. Perhaps there's other things going on with the health of these individuals, but we're starting to make a lot of guesses here. I'm starting to make a lot of guesses about what's going on biologically. So the data are significantly different from each other. The biological relevance can't say, and even if I were to repeat this experiment or Galton repeated this experiment, can't guarantee that we'd get the exact same results. So we'd have to get additional data, we'd have to repeat the experiment, we'd have to understand more of what's going on. And again, can't emphasize this enough. Statistical significance doesn't tell you actually what's going on biologically. It cannot tell you what's going on biologically. It will not ever never tell you about the biological relevance. Requires you to make inference and ideally requires you to collect additional information. Again, never will. Doesn't matter how much you hope it will. It never will tell you about biological relevance. You need to use other tools and repeats of the experiment to do that. Additionally, and similarly, statistical significance doesn't tell you about causation. It doesn't tell you exactly what is causing this. I'm proposing that maybe it's the amount of resources that each family had available to divide for their children, but there could be other reasons. Perhaps children who are in larger families are working on farms and working harder causes you to be shorter. Don't know. That doesn't seem very realistic, but we don't know actually what's causing here. So significant doesn't tell you that family size is exactly what's causing here. Maybe it's workload. Maybe it's exposure to parasites. If you're in a larger family, you're more likely to be in a rural environment, which means you're more likely to be exposed to parasites from animals. We don't know actually what's causing this difference, or if we were to repeat the study, whether the difference would occur. So Was it poverty and malnutrition involved here? Was it exposure to a rural environment? We don't know. So I will keep saying this and I will keep putting it in big red letters. Statistical significance will never tell you about the biological relevance or the causation. It's just telling you that the data have certain mathematical properties. And to go beyond that, you need to use logic. You need to use other experiments, ideally, to extend those findings. If you're taking this course, watching this video as part of a course, get ready to pause the video in order to answer the following question. So, looking at graph A on the left here, what can you conclude from this graph? Go ahead and read the options, pause the video, and answer in the course software. So, we have two means here. The error bars do not touch. We can conclude that there is a statistically significant difference. There's an important mathematical difference between these groups. However, we can't conclude any of these other things. We don't know whether the difference is biologically important. We don't know whether the difference is biologically relevant. We just know there is a statistically significant difference between the groups.